Okay, let's begin by saying that with proof, at the very outset, there's 4 different types of proof. And this is given to you on your handout. There is direct proof. Let's make that a bit bigger. Okay. So firstly, there's direct proof. And this is also known as proof by deduction. And this is where each step follows from the previous one, using some sort of accepted facts or results, okay, which is something I'll be talking to you about in a minute. The other one is proof by exhaustion. Okay, this is quite an easy one because all you're going to do is look at all the possible cases that have been specified to you. Okay, so for example, the numbers between 1 and 10, if you square them, then this happens. Well, that's easy. You can just take the numbers 1 to 10, do every single combination, and then come up with a conclusion. Okay, so that's the second one, and that's where you test all the possible cases and then come up with a reasonable argument. Number 3 is proof by contradiction. Okay, contradiction. And this is also, I'll write this down as, it is a proof, but it's an indirect proof. Okay, it's an indirect proof. And what you're doing is that if there's a statement, in order to prove that it's true, what you'll do is say, all right, what happens if it's not true, for example, right? And then you show that that statement, the argument that it's not true, will just lead to some sort of absurd result. It can't be true. And therefore, what you're saying has to be true. Okay? The only example that comes to mind at the moment, a non-mathematical one, is some sort of crime scene where somebody's lying on the floor, somebody's dead, it's established that they've been murdered, so it wasn't a suicide. There's 3 people in the room, and using the process of elimination, you're saying, well, it can't be person A, it can't be person B, and therefore it has to be C. I mean, how else does a person die? Now, you haven't directly proved that person C has actually committed a murder. You haven't actually explicitly shown that. What all you've done is indirectly shown that the only way the murder can happen is if C had done it. It can't be A for whatever reason, it can't be B for whatever reason, so it has to be C. The motive is there, and whatever. Explain that. So it's like an indirect proof. And that hasn't come up so far in the exam. Okay, but I'll be giving questions on it, so you should understand how it works. Question 4, the type 4, is not a proof; it's a disproof by counter-example. Okay, and all you're doing is finding one case where the statement doesn't work. If you find that case, you've disproved it. Okay. What comes to mind is a song by Whitney Houston. It's not right, but it's okay. Has anyone heard that? All right. I'll play it. So what we'll be doing today's lesson is to focus on proof by contradiction or indirect proof and a disproof by counterexample. Before we look at these proofs, we need some sort of toolbox. Okay, and this is what we have. So first, we need to be aware of odd and even numbers. So if n or k, okay, is some integer, then we know odd or even numbers will just be 2n, but odd numbers will be 2n plus 1. Multiples will be 3n, 4n, 5n, etc. Remember, n is just some integer. Consecutive numbers, n, n plus 1, n plus 2, and on and on. Yeah.
Didn't the odd user exclude 1?
Sorry?
Didn't the odd user exclude n is equal to 1? Sorry, no, I lied.
1 is an odd number.
Yeah.
So, and you start with 0, so you're not, yeah, okay. And then square numbers would just simply be n squared, n plus 1 squared, etc.
So can we go with B?
Yeah. Is that okay?
Yeah.
Rational numbers are written as follows, where A over B, where A and B are some integer and have no common factor. Okay, and therefore it must be a rational number if you write it as A over B. Accepted facts are things like the sum of angles in a triangle, also perpendicular lines, m1 times m2 equals minus 1. Proven results and laws are things like the index laws, the log laws, also the discriminant, d equals b squared take away 4ac, gives us the nature of the roots. So that's just proven. You don't need to go down and start proving this stuff. And theorems are things like, you know, Pythagoras' theorem, and the circle theorem. Okay, also, something that we can assume is a given, you don't need to go around proving it every single time, is even times even gives us what? Even. Even times odd gives us what? Odd. Odd times odd is odd. And then you could extend those results to...
Oh wait, doesn't even times odd give us even?
Yeah.
Even times odd gives us even. Thank you. Or even plus even is always going to be what? Even. What about an odd plus odd? Okay, it would always give us an even. And an odd plus an even will always be odd. And you can always take 2, 3, 4, 5 as examples where you try these out. And generally they hold, or they always hold. But you don't need to prove this. But we will be doing one of these proofs in a minute. But you don't need to always go down and try and prove this. You can just use them as accepted facts when you're doing a proof. Yeah. So let's look at some proofs by counterexample. A disproof. So disproof by counterexample. That's probably a good one to start off with. Let me just get the background to graph a bit big. Let's do that. That's a bit better. Okay. And let's just look at a couple of things. So, example 1. Say, is n squared plus n plus 41 prime for all values of n? So there's my statement. And what we have to do is, because we're going to disprove it, we just have to find one example where it doesn't work. And therefore we've disproved it. So what we'll do is put n equals 0, that gives us 41. N equals 1 will just give us 43. N equals 2, 2 squared 4, plus 2 is 6, give us 47. And so forth. So far it's working. However, if n equals 41, we'll end up with 41 squared plus 41 plus 41. And that essentially is 41 plus 2 times 41, or can be written as 41 times 43. which is not prime.
How can that be written as 41 times 42?
So 1,763 divided by 41. Sorry, 43. And so all we're doing is just establishing that there are 43, 41s inside that number.
So,
Yeah.
would you have to keep trying it?
Alright, let's look at another one. And this is quite a nice one because it goes back to our odd-even discussion. I'll write out the question. Given that x and y are positive integers, so with example 2, let's look at this one here. Let me do a different one. So let's put a statement down. The product of two unequal positive irrational numbers is irrational. Okay, there's my statement. And all I have to do is find a counterexample to disprove that. So all we need is two unequal positive irrational numbers. Let's take square root of 2, square root of 8. They're both different.
Irrational means it has it's two integers.
It's written exactly. It's actually.
Yeah, you cannot write it. So if you go back,
Write it as this
if you go back to the definition, a rational number can be written as a fraction where a and b are integers and have no common factor. But an irrational can't be, like square root of 2, pi, etc. Okay. So square root of 2 times square root of 8 gives us the square root of 16, which is 4. But this is a rational number. Yeah, so I've just found an example where I've got an integer, okay, which is not an irrational number. Let's move on to a proof. Let me just put this down. Okay. Let's move on to a proof. So this is not a disproof, it's a proof by a counterexample. Okay, and I'll run through a couple of these. Example. Okay, or it's also called an indirect proof. Okay. The one here, proof by contradiction. Sorry, let me put that down. Proof by contradiction. Let me use this time instead. Okay, or indirect proof. Now, in this sort of proof, let's have a look at the example I was going to do before, where given x and y are integers, show that x, y is an odd number if x and y is an odd number, then x and, it's not or, it's and y have to be odd. So what we're basically saying is odd, i.e. odd times odd gives you an odd.
But to say then x and y are both?
Positive integers. Okay? So x and y are positive integers. Show that the product of two positive integers, if it is odd, then x and y are also odd. Okay? Now, rather than proving this directly, we're going to prove it indirectly. And we start by doing something which is contrary to the condition given to us, i.e. x and y are both odd. So let's assume that we break this condition, x and y both have to be odd. Let's assume x and y are not both odd. So i.e. let's make x is even, and therefore x equals to m, where m is some integer. Now xy therefore is going to be 2m times y, and we know 2my is even.
So why does m have to be an integer?
So 2my is even, which is contrary to what is required. Therefore, x can't be even, and for that reason, y can't be even, and xy, so if xy is to be odd. Right, because in this case, all we're doing is considering integers. We've specified it at the beginning, and that's what we're dealing with. There's no point of trying to create a complication where m could be some sort of fraction. It doesn't do anything. It doesn't help us in the proof in any way whatsoever. If the whole problem involved fractions or irrational numbers, then fair enough. But it doesn't. We're just dealing with integers. We go on to our next proof. Let's just look at what's happened. We've had a statement. Rather than take it on heads on, by the horns and say, right, let's go and prove this algebraically, we've said, all right, what happens if this condition doesn't hold? What happens if x and y are not odd? One of them is even, for example. And the same applies, obviously, if both of them are even. If I've got 2m for x, y can be 2p. I'll end up with 4m times p, which is always going to give me an even number. Okay, and so therefore what I've done is it was essentially said indirectly that if that condition doesn't hold, then it can't be odd. It leads to an absurd, the whole thing doesn't work. Therefore, both of them must be odd. So odd times an odd would give us an odd. Let's look at another one. Okay, let's have a look. This is quite a nice one. Let's prove the square root of 2 is irrational. The square root of 2 is irrational. Prove it. To prove it indirectly, i.e. by contradiction, we set up we go outside the condition stated and show that that leads to an absurd argument. It doesn't work. So we say, let's assume, LETS. So let's assume the square root of 2 is rational and see what happens. If the square root of 2 is rational, then we can write this as a over b, where a and b have no common factors. So two integers have no common factors and are therefore what we'll term as co-prime. Co-prime is just a word that means they don't have any common factors. Integers, yeah. In other words, it's a rational number. Square root of 2 is a rational number. You can write it as a over b, where a and b are some sort of integers. Now, if that's true, then 2 equals a squared over b squared. Now, watch this. So this is now closing into the argument. And a squared, therefore, equals 2b squared. If a squared is 2 times any integer squared, 2 times any integer is always going to give me what sort of number? Odd or even? 2 times any integer, 2 times 3, 2 times 4 is always an even number. And therefore, a squared is even. And so, I can write a equals 2k, where k is some integer. So a squared equals 4k squared, and this equals 2b squared. But hang on a minute, if that's true, then b squared equals 2k squared, and therefore b is what? If b squared equals 2k squared, where k is some integer, b must be what sort of number? Odd or even? B is even as well. If A and B are even, they have a common factor. Exactly. They have a common factor. And therefore are not co-prime. And this contradicts the assertion. Therefore, the square root of 2 can't be written as a fraction. Oops. And is not rational. Right. Can we have a go at these two questions here? So I'll put down questions 1 and 2 from the worksheet I've given you. So what I'd like to do is find a counter example to disprove this. Now, if you look at the questions on the worksheet I've just given you, from questions 1 to 10, it's all about disproof by counter example. Questions, can you make a note of this, please? Questions 11 to 15 are proof by contradiction. Now, questions 11 to 15 I'll probably put down as optional. They're not compulsory. I'll say do the first couple. Do at least 2 questions from 11 to 15. But from 1 to 10, do all of them. Okay, so the disproof by counter example is something you need to understand and do. The proof by contradiction, something can be quite lengthy. It's something you should just appreciate and understand. Okay, but I wouldn't stress too much about them. Like I said, they haven't come up in an exam before, but that's not to say it can't come up. Okay.